Hey students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need something, please send me an email and I will do whatever I can to try to help. So lucky you get to hear my voice for another lecture. But the best part is we're going to be doing another example on how to use the 4 steps of hypothesis testing when you have the population mean and the population standard deviation. Yay! So here are the 4 steps to hypothesis testing. Let's talk about each one just as a brief review. The first step is to write your hypotheses. You're going to write your null hypothesis, which is the one that describes the status quo, what we expect in the population, and you're going to write your alternate hypothesis. The alternate hypothesis addresses the question. Whether you're working with proportions or you're working with means, you're going to use the notation that describes the population parameter. The next step is usually the longest step, and that is the prepare step. So during the prepare step, you're going to do a variety of things. You're going to choose the significance level, and you're going to find the test statistic for that significance level. To do this, you will also need to decide whether you need a 2-tailed or a 1-tailed test. And if you need a 1-tailed test, do you need a left 1-tailed test or a right 1-tailed test? You may have to calculate the standard error for your sample during this time as well. You might also need to check the assumptions to make sure your data is normal. So unless something is already stated in the problem that tells you to assume normality, then you would have to check for the conditions of the central limit theorem. This is also the time where you want to make yourself a model and establish the area of rejection and the area of retention. The next step is the compute to compare step. In this step, you are going to calculate your Z obtained using the sample information, the population information divided by the standard error that you calculated for your sample. Once you calculate your Z obtained, you will compare it to the test statistic that you got in the prepare stage, which is called the ZCrit. And also, you're going to compare it with the model that you created. If your Z-score falls in the area of rejection, this is evidence that the null should be rejected. Also, this is the time where you will calculate the p-value for your test statistic, for your Z obtained. If the Z obtained's p-value is less than your significance level, or your alpha, then you should reject the null hypothesis. It's important that your obtained Z falls in the area of rejection, and also your p-value is less than your alpha. If you get mixed results, something went wrong. In the last step, you're going to decide whether you will reject or whether you will fail to reject, in other words, retain the null hypothesis, and you state your conclusion in the context of the study. In this example, we're going to work with body temperatures. So here's the background information. In the 1800s, German physician Karl Reinhold took millions of axillary, that means armpit, temperatures from soldiers. This study established that body temperature is normally distributed, and the standard normal human body temperature is 98.6 degrees Fahrenheit with a standard deviation of 0.72 degrees Fahrenheit. In a recent study, British researchers obtained 25,000 axillary temperatures from a London hospital. The mean of these temperature readings was 97.9 degrees Fahrenheit. Assuming a type 1 error risk of no more than 1%, did the findings support the theory that human body temperature has decreased since the 1800s? Once again, I've gone ahead and cut-pasted the 4 steps for null hypothesis statistical testing, and I've also cut-pasted the question into Ziteboard. And if you remember, I always put the link for the Ziteboard in the description box, so you'll be able to have that. I want to make sure that I stay consistent, so I have been writing the hypothesis in green. I've been writing the prepare in red, the compute to compare in pink, and then finally writing the interpretation in black. So I'm going to go ahead and stay with that again. So I'm going to go ahead and read the scenario back to myself. I like to read it several times because I want to make sure that I understand everything. It says that in the 1800s, so a long time ago, this German physician took a ton of temperatures, and he took the temperature from the armpit of soldiers, and he established that the normal body temperature is 98.6 degrees Fahrenheit with a standard deviation of 0.72 degrees Fahrenheit. Okay, that's what's known. Now, in a recent study, these British physicians, researchers, whatever, they took 25,000 armpit temperature readings from patients in a London hospital. And when they calculated the mean for these temperatures, they got that the temperature reading was 97.9. And we want to assume no more than 1% type 1 error risk to see if there's enough evidence that would support the theory that the human body temperature has decreased since what it was in the 1800s. Okay. All right, so let's start with our hypothesis. So I want to write my null hypothesis and my alternate hypothesis, and this time we're working with means. So the population mean is always written with the symbol of mu. So I've got mu, and it has been established that the normal human body temperature is 98.6. So that's what it is right now. That's what we believe it to be. Degrees Fahrenheit. Okay. And they want to know if it has decreased since when this reading was originally established. So we want to know if mu is less than 98.6. Okay, so that's my first step, is writing out the null and alternate hypotheses. The next step is to prepare. And as always, I like to go ahead and write out the things that I may need. So we have the mean here, which was our mu, but they also told us that the standard deviation for our mu was 0.72 degrees Fahrenheit. And they told us that in this new study, there were 25,000 temperatures taken. So that's going to be my sample size. And when they calculated the mean of these temperatures, they got the mean of the sample to be 97.9 degrees Fahrenheit. And they want us to assume no more than a 1% type 1 error risk. So we want our alpha to be 0.01. And it's telling us up here also that look, that the temperatures are normally distributed. So we do not have to test for normality. We can assume normality because it's already in the problem. So that makes it nice. We have one thing less to do. Okay, we assumed normality. We've got all the pieces we need. We need to figure out what kind of test we want, and we need the ZCrit. So this right here, they're looking for things to decrease. Okay, they're looking to see if this has decreased. They don't want to know if it increased. They just want to know if it decreased. So if we're looking at a normal curve, and our mean right here is going to be 98.6, and we want to know if there has been a decrease here from 98.6, we're going to be looking over here at the left tail. Because that's where we're going to expect to see a lower number, right? So I need a left one-tailed test. So I'm going to need a left one-tailed z-test. Okay, cool. And now I'm going to need my ZCrit, so that I can mark where the region of rejection ends and where the region of retention starts. So I'm going to go ahead and go to my ZCrits scores, and I'm looking for a left one-tailed hypothesis, and this time I'm looking for 1% alpha. So here my 1% alpha ZCrit is going to be negative 2.326. So I'm going to go ahead and go back to my Ziteboard and write down that my ZCrit is negative 2.326. So if I were going to mark that here, right, here is 0 z-score, 1, 2, 3, negative 1, negative 2, negative 3, then negative 2.326 is going to be right about here, approximately, maybe. And everything that is on this side, I'm going to reject. And anything that's on this side, I'm going to retain. Looks great. Okay, now I need to know where is my standard error, right? I have my standard deviation, so that makes it really nice because I can use the standard error formula, which is so much more simple than the proportion one. We're just looking for the standard deviation divided by the square root of the sample size. So my standard deviation is 0.72, and I'm going to divide that by the square root of, what's my sample? 25,000. Awesome. So let's get some Google Calculator action here. Make this little guy a little bit smaller. Okay, here we go. We've got 0.72 divided by the square root of 25,000. Enter. And I get a standard error of 0.00455. So my standard error equals 0.00455. Very small. Awesome. I'm looking really good here. I've got figured out where I'm going to retain and reject. Got my standard error, got my ZCrit. Now I've just got to start computing and comparing. To compute and compare, I've got to figure out what my Z obtained is, and then I need to find the probability of getting a Z obtained of that size or smaller. So let's start with our Z obtained. So my Z obtained is going to be the difference between my mean from the sample and the population mean and the standard error. Okay, so my sample mean was 97.9, and from that I'm going to subtract my population mean, which was 98.6. It's what we use to write our hypotheses. And then I'm going to take that difference, and then I'm going to divide it by 0.00455, which was my standard error. Okay, alrighty. So here is my Google Calculator. I'm going to go ahead and make him just a little bit smaller so I can see everything. Okay, here we go. And I'm going to clear this out. So I've got 97.9 minus 98.6 equals, and I'm going to divide that by 0.00455, and I get a Z-score of negative 153.8. Now you're probably thinking, how is that possible? Oh, it's possible. What does it mean? It means that I just had to get past negative 2.326, right? That was this line right here. That was negative 2.326. And not only did I pass it, but I way passed it. I'm all the way out here, somewhere out here at negative 153.84, right? This is negative. Got so excited I forgot to write the negative sign. So it's all the way out there. Very, very different from the mean. All right, so let's see what the probability is of getting a z-score that is negative 153.84. And can you think to yourself what that might be? What do you think? I'm going to look at the mean, which was 98.6, and this is the mean of the population. Instead of standard deviation of the population, I'm going to use the standard error of the experiment, and that was 0.0046, okay? And I want to know what is the probability of getting 97.9. So let me just go over these steps again. Here I have what is in the center of the curve, right? So the population mean, 98.6, would be in the center of the curve. We're not working with standard deviation, we're working with standard error. And the standard error for this sample, we figured it out by taking the standard deviation of the original study and dividing that by the square root of the sample size. And so we got the standard error of that sampling distribution to be 0.0046. And we want to know, if that's the way that we've created the curve, what is the probability of getting a score that is less than 97.9? When we hit compute, and basically here's my curve, and this thing is all the way over there. See that? There is no chance of that happening. Basically nothing. 0% chance. So the probability of getting that Z obtained is 0. So when we're looking at the results, at the end of the day, we have enough evidence that we can reject the null. This is statistically significantly lower than the presumed body temperature standard. In the last step, we want to make sure that we can write our findings in the context of the question. So let's go back and read the question again. In the 1800s, German physician Karl Reinhold took millions of axillary temperatures from soldiers. This study established that body temperature is normally distributed, and the standard normal human body temperature is 98.6 degrees Fahrenheit with a standard deviation of 0.72 degrees Fahrenheit. In a recent study, British researchers obtained 25,000 axillary temperatures from a London hospital. The mean of these temperature readings was 97.9 degrees Fahrenheit. Assuming a type 1 error risk of no more than 1%, did the findings support the theory that human body temperature has decreased since the 1800s? So in the context of the study, we can say the findings of the recent British study of 25,000 patients in a London hospital suggest that the human body temperature is statistically significantly less than the accepted standard of 98.6 degrees Fahrenheit established in the 1800s. I'm going to go ahead and quickly recap this, but you know I'm going to read this question again because I haven't read it enough, I guess. So the scenario is, in the 1800s, German physician Karl Reinhold took millions of axillary temperatures from soldiers. This study established that body temperature is normally distributed and the standard human body temperature is 98.6% Fahrenheit with a standard deviation of 0.72 degrees Fahrenheit. In a recent study, British researchers obtained 25,000 axillary temperatures from a London hospital. The mean of these temperature readings was 97.9 degrees Fahrenheit. Assuming a type 1 error risk of no more than 1%, did the findings support the theory that human body temperature has decreased since the 1800s? In the hypothesis phase, I went ahead and wrote down the null and the alternate hypotheses. The null hypothesis was what we expect to happen all the time, and it already said in the scenario that the accepted body temperature was 98.6. So the population mean is 98.6, and I went ahead and wrote it right here. Since we were asked to look at the study's findings and determine if there was a statistically significant decrease, then we wrote the null hypothesis as mu is less than 98.6. In the prepare stage, we went ahead and just started to list out what we knew. So over here, we knew that the population mean was 98.6. That's what we had used to write our hypotheses. And we were also told that the standard deviation for the mean was 0.72 degrees Fahrenheit. We knew that the sample size was 25,000 and that when those readings were averaged, the mean for the sample was 97.9 degrees Fahrenheit. The scenario asked us to make sure that we did not risk more than 1% of committing a type 1 error, and we were looking for a decrease. We were looking to see if that had decreased, if the temperature had decreased. So with that information, we knew we needed a left one-tailed test, and we needed to find the ZCrit for a 1% alpha for a left one-tailed test. So I went into the ZCrit lookup table that is in the description box below, and we found that the ZCrit for a left one-tailed z-test with 1% alpha was negative 2.326. Now, we went ahead and drew out our normal curve, our model, and decided that right here, negative 2.326 was the boundary. Anything that was less than that, we were going to go ahead and reject that. Anything more than that, we were going to go ahead and retain that. The last thing that we needed to do before we could start comparing and calculating things was to determine the standard error. And since we were given the population standard deviation, we could just use the standard deviation divided by the square root of the sample size to find our standard error. Super easy formula. So I went ahead and put in 0.72 degrees Fahrenheit in the numerator and the square root of 25,000 in the denominator, punched that into Google Calculator, and I got that the standard error was 0.00455, and if we were going to round it, 0.0046. The next step was to compute and to compare, and the Z obtained was calculated by taking the sample mean, and from that I subtracted the population mean, so I took that difference, and then I divided that difference by the standard error. So when I plugged in numbers, I just put in 97.9 minus 98.6 for my numerator, figured out what that was, and then divided that by 0.00455, and I got that the Z obtained would be negative 153.84, which is much, much, much less than our ZCrit, which was negative 2.326. It was further to the left, much further to the left. I also went ahead and calculated the probability of obtaining that z-score, and I put that into the probability calculator, and the output told me that there is pretty much no chance that it was due to normal variability. Since 0 is less than 0.01, then we are going to reject the null of no difference, and we're going to assume that the alternate hypothesis is correct. Finally, we went ahead and put the findings in the context of the study, and we wrote that the findings of the recent British study of 25,000 patients in a London hospital suggest that the human body temperature is statistically significantly less than the accepted standard of 98.6 degrees Fahrenheit established in the 1800s. So what's the big idea? The big idea is that the 4 steps of hypothesis testing provide a systematic process to answer a research question concerning the population parameter. The 4 steps are hypothesis, prepare, compute compare, and interpret. So That's it for today. Don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher Tora saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!